Hi, I'm Nico Pietroni from the University of Technology Sydney, and I present a new paper on quad meshing with feature line preservation. This paper is a joint work with Stefano, Thomas, Paolo, and Marco. Quad meshes have multiple applications in computer-aided design, architecture, and entertainment industry. But what are the main objectives for a nice quad meshes? First of all, we aim for nicely shaped elements. Usually, we want also the edges to be aligned with curvature lines. We look for uniform tessellation density, and also we aim for a good irregular vertices layout. Finally, we want also to preserve the feature lines. Those are the main objectives for most of the quadrangulation methods that has been proposed in the last decade. So, while state-of-the-art methods mostly succeed in satisfying the first four objectives, they usually fail to preserve the sharp features for the general case. For example, this method, it cannot represent all the sharp features, and the final quadrangulation miss some of the features. The quadrangulation method here shown in the second part of the slides can create the generated element. Or some method can also insert an excessive number of irregular vertices. That happens because most of the quadrangulation-based methods try to derive a global parameterization and then stitch some of the feature lines using hard constraints or iteratively. Instead, we can successfully preserve all the feature lines, since our method is designed around feature lines. So here you can see some of the examples that has been successfully tessellated with our method, and we proved the robustness of our method testing it on a database of 10,000 models which is available on the net. Here we show an overview of all the models we were able to tessellate. Our method belongs to the class of methods that first subdivide the mesh into patches and then quadrangulate each patch individually, like the method proposed by Marcel Kampen and colleagues in SIGGRAPH 2012. So, let's overview our pipeline. We start with a triangle mesh with marked feature lines, and then we construct a cross field with state-of-the-art methods, using, for example, the method proposed by Diamanti and colleagues. Then we derive a patch layout, and finally, we tessellate each patch individually, but in a way that they are globally consistent across the whole mesh. Because we want our course layout to embed arbitrary feature lines and also to be aligned with the fields, we need to be very permissive with its definition. We include, for example, both rectangular and non-rectangular shapes. For example, patches with 3 sides or patches with 6 sides. We also include T-junctions. But before going to explain how we can derive a nice patch layout, let's first describe how we can tessellate a patch. Let's, for example, consider first a simple rectangular patch. This is a trivial case, for example, like the one shown at the top left corner, where opposite sides have the same number of edges. In this case, we can simply quadrangulate the patch with a regular grid. If this is not the case, we can still quadrangulate the patch if the sum of the sides is an even number. So, to this purpose, we can use the method proposed by Takayama and colleagues. Clearly, the regular case is to be preferred because it inserts fewer irregular vertices. So when a patch is not rectangular, The ideal case is when you can tessellate it with a single irregular vertex. We say that the patch is Catmull-Clarkable, and we can Catmull-Clark the patch. We can tell if this is the case by just looking at the number of subdivisions on the side and apply the same rules, some simple rules, which are defined in the paper by Tarini in 2021. For example, these triangular patches with 13, 9, and 8 edges is Catmull-Clarkable according to the rules, and so we can tessellate in an ideal way by placing only one irregular vertex on the interior. Instead, applying the same rules, we know that this triangle with 10, 2, and 14 subdivision on the side cannot be tessellated in the ideal way. In this case, we can still use the approach of Takayama and colleagues to create a consistent quadrangulation. But again, this is not the ideal case because it inserts extra singularities in the interior. Similarly, we can tessellate the pentagonal patch with a single irregular vertex. And we can derive if it's possible by looking only at the subdivision on the side. Again, if the rules of Catmull-Clarkability is not verified, we can actually still rely on the approach of Takayama and colleagues to produce a final quadrangulation. But again, this is not the ideal case. So in general, we can tell just by looking at the number of edges if a patch can be tessellated with a single irregular vertex or not. Okay, now, in order to get a consistent global quadrangulation in our method, we solve an ILP. So, first of all, to encourage isometry, we need each arc to be as close as possible to its ideal size. So we add an energy term to favor this isometry. Also, to encourage the ideal tessellation of quadrilateral patches, we need to encourage that the opposite sides of the quadrilateral patch to have the same number of subdivisions. Similarly, we can encourage the ideal tessellation of non-quadrilateral patch by using our Catmull-Clarkability criteria. So this is true for 3, 5, and 6 patches. And this set of rules are expressed in this paper by Tarini, 2021. Finally, to admit a quadrangulation, the sum of the sides of each patch should be even. Next, I'm going to summarize the main phase of our quadrangulator, which is how we can derive a nice patch layout. So we actually derive a nice patch layout by adding one feature lines, one path at a time, until a good layout is obtained. So we use a set of heuristics to choose the lines and to choose the path. However, before I'm going to explain it, I need to explain the criteria that we use to determine when a patch layout is good. First of all, we need each patch to be homomorphic to a disk. Then, in order to use the tessellation by Takayama and colleagues, we need the valence of each patch to be between 3 and 6. Also, we want each corner to be convex, like the one shown on the top patch, not the one shown on the bottom patch, which has a concave corner. We want to favor the patches that can be quadrangulated with no or a singular irregular vertex, according to our Catmull-Clarkability constraints. Also, we want the patch valence to match with the valence of the singularities of the underlying field. Finally, patch layout should be coherent with the underlying cross field, means it more or less to have the same orientation. So to derive a patch layout, we have a set of constraints to be satisfied. However, some of them, they have to be satisfied in a hard manner, so they are mandatory to obtain a quadrangulation, while others can be satisfied in a soft manner because mainly regards the beauty of the final tessellation. Okay, if we look back at the initial example, we see that this example, just looking at the initial feature line, it breaks most of the rules that we already defined. For example, we can have concave angles in the initial features. Also, we can have some pointy features, like those one shows on the slides. So how we can address these issues to get a nice patch layout? So let's see, for example, how we can ensure the corner to be convex. So if a corner is convex already in the initial feature, then it's fine. Also, every point belonging or every side belonging to a straight line, that's fine as well. However, if we have a concave corner, we need to split it into a convex and a straight line by just adding a path. Similarly, for a pointy corner, we can simply add one feature lines to get to straight lines. So with this simple set of rules, we can obtain convex corners from the initial feature layout. Notice that the classification of the corner is purely based on field topology and requires no geometric test. So to finally create the remaining patch layout, similarly to looping cut, we add one path at a time using a greedy strategy that distributes them uniformly and then try to match at the same time our main constraints, main criteria. Then we can remove the redundant patch in reverse order, being sure that the criteria are still satisfied. And that's the final patch layout for this mesh. We use the same tracing approach of Quad Mixer for tracing path, which is quite robust and efficient. Moreover, this tracing procedure also allows us to verify the consistency of crossing between paths in a combinatorial way. However, this method assumes to have a decent meshing to start with. So we perform an initial remeshing using a variation of the approach proposed by Opp and colleagues, supporting adaptive tessellation and sharp feature preservation. We tested our algorithm on several examples of mechanical objects like the one shown here in the picture. As you can see, our method is able to preserve the feature lines at the same time get a globally consistent and nice quadrilateral tessellation. Our method can successfully tessellate mesh with complex features like the one shown in the picture. For example, here you can see that there's these feature lines that forms a very sharp angle on the surface. One interesting feature of our method is that it actually uses two kinds of irregular vertex. So we can place irregular vertex at the corner of the patches, including the ones that are on the feature lines, plus our system also adds additional irregular vertex inside the interior of each patches. Those irregular vertices are needed to get the final consistent quadrangulation. However, while the vertices on the boundary of the patches are reciprocally aligned by construction, the wire inside the patches can not. In general, they are not aligned. So, because our cut-mult crackability constraints allows us to define the position of the irregular vertex inside the patch, we can favor the alignment of irregular vertex along adjacent patches by setting a set of linear constraints in our ILP. You can see the details of these constraints in the paper. Here we show some other results with challenging shapes. So this is one shape that we tested and belongs to the database of 10,000 meshes which is available on the net. In this case, our method was able to obtain a nice quadrangulation and preserve all the feature lines. Also, considering that the quad sides are quite big with respect to the sides of the feature that are presented on the mesh, which means that our method is quite robust, as also testified by this mesh here, which has a lot of feature lines, and our method can successfully tessellate it and preserve all the feature lines at the same time. So here we show another example, which I consider an extreme example. You can see here it's like a mesh with high genus and a lot of feature lines. Even in this case, our method can successfully produce a nice tessellation, at the same time represent all the feature lines that were in the input mesh. So our method also has some limitation. First of all, if the input lines, if the input features are noisy, right, then we will propagate this noise over all the pipeline. And in the end, this noise will be also reflected in the final quadrangulation, as you can see here. Second, we only consider the length of the sides of a patch to see if the patch is nice or not. And in this case, for example, we cannot see that, for example, this patch has a strange shape on the middle, or it's not quite uniformly sized as a rectangle, just by looking at the side length. Finally, I would like to thank my fantastic collaborators, Stefano, Thomas, Paolo, and also Marco. And I invite you to see the final result on www.quadmesh.cloud.